That's the one. Okay. All right.
Hello, everyone. Thank you so much for joining us for the last colloquium of this semester. Today's speaker is Monika Lendl. She obtained her PhD in 2014 from University of Geneva. And after that, after one postdoc in University of Belgium, she spent several years as a PI of the GERAPO project in Austrian Academy of Science. In 2019, she back to the University of Geneva, and since 2021, she is as assistant professor in University of Geneva. Her study is focused on detection and characterization of long period planet, and also detectability of the Earth-like planet in upcoming telescope plateau. She also studied the climate of the atmospheric climate of the highly irradiated planet, and she is part of the CHEOPS science team, and she is also a mission scientist. Thank you so much for joining us today. The stage is yours.
Okay, well, thank you so much for the invitation. It's really great to be here, and yeah, what a beautiful time of the year to visit Paris. Okay, but I'm not here to do sightseeing, at least not yet. But I'm here to tell you about what we've been doing with the space mission that you can see here. Let me see if this, yeah, beautiful. Okay, so a space mission called CHEOPS, that's short for the Characterizing Exoplanets Satellite, that has a bit under a year ago completed its nominal mission and is still in the sky and observing exoplanets. All right, but let's start a bit closer to home. I'm sure you know these friends here are the planets of the solar system, and of course they're beautiful. They inspire us. We can actually go there, or at least send spacecraft there. They can take measurements in the atmospheres of these planets. We can photograph them up close. We can even land on them, collect samples, and hope to bring them back to Earth to analyze. So of course, this is a wonderful playground. However, when we look towards other stars and the planetary systems around these stars, well, the situation is quite different, right? So when we go and we want to study exoplanets, well, we have to do with a little less. So what about exoplanets? Well, the kind of best pictures we have of exoplanets would be something like this. This talk is not about directly imaged exoplanets. There's a couple of them, but there are still preciously few systems. Yeah, they're basically essentially young systems with very massive far-out planets. And these little blobs you see here, of course, do not have any spatial resolution. That's all the light of the planet mixed together. On the other hand, the way we've been discovering and studying exoplanets largely over the last 20 years, that has been through indirect methods. Now, I know not everybody here is from the domain of exoplanets, so exoplanet scientists, please feel free to go in a very short slumber. But the two techniques that we use are pretty straightforward, actually. Let's first look at the transit technique. Well, we look at a star that is far away, and what we're measuring is the integrated flux. Now, if planets pass in front of the star, they obscure part of the stellar photosphere. We register less flux, and we observe this characteristic drop in the stellar brightness. We call this the light curve. And the amplitude of this drop, well, that's directly proportional to the size ratio of star and planet, the area ratio. And then, of course, as soon as we know something about the star, which is not that difficult, we have a good measurement of the planetary radius. The other technique, and the pioneering technique really of exoplanet discovery is the radial velocity technique, where we observe a planetary system as star and planet orbit around their common barycenter, and we measure precise Doppler shifts in the stellar lines. And then, since the star moves, right, we don't actually see the planet, we just see the movement of the star. These lines, they shift blue and red, and what we're registering is a beautiful periodic variation in the radial velocity of the star. And then the amplitude of this variation, of course, is related to the planet to star mass ratio. And having a bit of knowledge on the star, well, that gives us a measurement of the planetary mass. So these techniques together have allowed us to detect and in a first order characterize a lot of exoplanets. So this talk here is not about radial velocities. That's a whole other subject, and there's plenty of experts that can give you a detailed talk about that. But what I'm going to talk about is planets that we study with this transit technique, so with photometric methods. But let's first do a little bit of a summary of the evolution of the exoplanet field. And I think there is no better way to do that than just look at a little movie that tells us about the planet discovery. So here on the y-axis, we just registered a mass or a mass estimate for the discovered planets, and on the x-axis, the period. And the dots that you can see there, well, those are the solar system planets. So maybe just keep an eye on this guy here, that's Earth, and up there, that's Jupiter. All right, so let's now let the timer run and observe how we are first discovering massive planets up here, and then with time, we're starting to fill up the parameter space down to planets with masses similar to that of the Earth. What you can see also in color here, you can see the radial velocity planets, the ones that don't necessarily transit their host stars. They're more sensitive to the longer period planets, but the transiting planets, they kind of cluster towards shorter periods. But here we're really also sensitive to some very small planets. And there. All right, hello. Okay, so just looking at this diagram, actually, we can already make a little bit of a zoo, right? We like doing this, we're astronomers. So we can say they're called Jupiters. These are the sort of planets that, were generally expected to be found without any prior knowledge because they resemble the gas giants of the solar system. But then there was this population of hot Jupiters. So these planets are weird. We're looking at planets of about the size and the mass of Jupiter, but look at their orbital periods. They have orbital periods of just a couple of days. So these are gas giants that have been moved somehow very, very close to their host stars, and they are basically being grilled by the strong irradiation from their host star. And then there is this block of planets that seem to be very abundant. They are smaller than the bona fide gas giants, but they are bigger than what we'd expect just from a rocky composition. So we call these planets Neptunes, but also sub-Neptunes, because many of them are actually quite a fair bit smaller than Neptune. And what is interesting also here is that many of them exist at orbital periods of a few days or tens of days out to a year. And this is, of course, very, very different from the ice giants in our solar system that are located out at periods of 100 years. And then, of course, we're discovering more and more small rocky planets. Okay, so just looking at this diagram, actually, we can already identify a few questions, a few things that we'd like to understand better about exoplanet systems. The first and maybe the most obvious one is this one, like how actually does it happen that we have these massive gas giants very close to their host star? We don't expect that they formed there. So probably the planets formed somewhere out there where there was a lot of cold, abundant material in the protoplanetary disk. And then somehow they migrated, they moved in to become hot Jupiters in the early stages of their lives. So these hot Jupiters, they're great because they're very hot, they're close in, they have frequent transits, and so they are very characterizable. And I will be talking much more about them. And here it's very, the things that interest us are to understand how their climates are shaped by this very intense radiation from the host star. How do the wind structures on these planets work? Do they transport the energy around the planet? What's the role of mass loss at this very high irradiation? And of course, I've already mentioned this, how do we actually get there? And if we're measuring the composition of these hot Jupiters, is there anything that we can say about how this process may have worked? Which parts of the protoplanetary disk these planets may have passed through in their youth? Then another thing, looking at this plot, right? We're seeing a lot of long period planets already, particular those ones up here. But what we're missing at the moment are the Earth analogs. You see Earth is down here. And there seems to be sort of a cutoff over there. And now this cutoff is not, it's not intrinsic to the exoplanet population, but it's really just a bias of our methods. The methods that I've shown you, the radial velocities and the transit method, they just are currently not yet capable of probing efficiently this area down here. So currently there is still little that we know about long period, low mass planets. There are very few transiting planets down there that we know. We don't know if these planets resemble the solar system planets. Our system architectures, like the solar system with outer gas giants and smaller inner rocky planets, are they actually common or more of an exception? And of course, our Earth analogs, planets orbiting solar-type stars with a period of 300 and something days and the size of the Earth. Are these common? That's still a very open question. And then finally, there's this region down here. I've already mentioned this, right? We have these Neptune or sub-Neptune planets that existed at pretty short orbital periods, period in abundance. And we don't have them in the solar system. So what is the origin of these planets? How do they form? What are they made of, actually? Are these rocky cores with a hydrogen envelope? Or are they more Neptune-like? Do they have a more higher metallicity atmospheres? Are they perhaps water worlds that have kind of a global ocean? So these are also still very open question, and also, of course, their formation. All right, so there are two space missions out there currently that are very active in answering these questions. And I'm sure you've heard already a lot about this one here. You've probably heard so much about this one, it's kind of coming out of your ears and you go like, oh my God, not again. So rest assured, we're gonna talk about the small one. So what I've just done here is like, I kind of made an almost correct size comparison. The JWST has a mirror diameter of 6 meters, of course, very large, fantastic. But CHEOPS has a mirror diameter of only 30 centimeters. So I'm really here to convince you that even with just a 30 centimeter mirror, you can do very interesting and very relevant science. Okay, so what is CHEOPS? Well, you can see CHEOPS there on the right. It's the Characterizing Exoplanets Satellite. It does one thing, but it does it extremely well. And that one thing is photometric measurements. So these measurements that we're using to measure the slight dimming of the stars when the planets transit. CHEOPS is a collaboration of 11 European countries. You can see the different contributions down here. And notably also, France has made a significant contribution to CHEOPS, and we have at least one member of the consortium in the room. Okay, it's a 30 centimeter optical photometric telescope. So we have a broad optical bandpass. It's an S-class mission, which means a small mission. It was actually the first mission of this kind. And it meant that we had to go very fast from adoption to launch in 5 years. But we did it. Everything was there was no technology development. We used methods that were already established, and we're also a pointed mission. So in contrast to other transit surveys, we really observe 1 star at a time. And if you're into photometric noise, these are sort of the precisions that we can get. So just to show you down here, that's over 3 hours. We're at slightly below 10 parts per million. So that's pretty decent. All right, so CHEOPS was adopted in 2014. Here's a couple of images of the satellite as it was being put together and tested. Then in 2019, CHEOPS was launched at 5:49 from French Guiana spaceport. And then there was, of course, commissioning, testing, and the science observations started in March. We had our first result, and I'm going to show you this later on, just after. And now in 2023, in September, we reached the end of the nominal mission with more than 16,500 orbits, over 250 targets studied. And we're actually not in retirement, but we have an extended mission that is running until the end of 2026. If you're interested in sort of where CHEOPS is and how it's doing, well, what you can see here is the orbit that CHEOPS was put in. It's a 700-kilometer low Earth orbit. CHEOPS is, of course, always pointing away from the sun, orbiting over the day-night terminator of the Earth. All right. So let me show you a couple of science highlights from the CHEOPS mission. And I have to say, this is really my personal biased selection. There are plenty of other fantastic results from CHEOPS that I am not going to talk about. But this is just because we've been up there for 4 years and I have only just under an hour to tell you about it. So one of the interesting things I've already alluded to is the composition of low-mass planets, right? What are these planets at this transition between rocky and gas giant actually looking like? What are they composed of? What is their exact mass radius relationship? And does it depend on any of these additional properties that these systems live in? So here there was a very interesting system that we observed pretty early on in the mission. You can see it, the 2 host stars compared here. So we looked at a K-type star. And the funny thing was that the NASA TESS mission, which is a mission that does sort of an all-sky survey, it identified, a very weird thing, it identified 2 planets that seemed to have almost the same orbital period. So we were suspecting that this might perhaps be the first exotrojan system out there. The orbital periods were just under 11 days. So to confirm it, well, simple, we take CHEOPS, we look at it for 11 days, and we should see transits of both planets coming. Now that's the light curve we observed. What we didn't see was one of these signals, the signal of the slightly longer Trojan planet. It was just not there. The transit wasn't where we expected it. We did see the other one though, the 9.9-day period. We saw it very clearly, indicated in pink here. And we also saw the inner planet that was already known before. Very deep, very clear transits with a period of 6 days. But then because CHEOPS is much more precise than the original discovery mission, we actually saw additional signals of much smaller planets. So we saw a signal at 3.2 days indicated in yellow here that just popped out of the data. And then looking even a bit more closely, we actually found another planet even smaller with a period of 1.9 days. So we killed one, we found 2 back, but then we went back to the drawing board and tried to understand why we originally thought there were 2 planets at a period of about 10 days. And well, it turns out that there are actually 2 more planets in there, one with 50 days and one with 20 days. And the timing of these transits just coincided conspired in a strange way that it gave us the impression there was another 10-day period out there. So altogether, what we found here was actually 6 planets, a system that contains 6 planets, and all of these 6 small planets, well, they fit within 0.13 astronomical units. That's about 20 days in orbital period. So this is an extremely compact system. And even more interestingly, the outer 5 planets, they form a resonant chain. So the planets have resonant orbital periods. And this means that the system probably hasn't changed its architecture greatly since its formation. So somehow these planets must have formed in the protoplanetary disks in this configuration and then moved in concert. Of course, we went further and we looked now the mass radius relations of these planets. And you can see that down here, the planets are indicated in green. And we can see that some of these planets, they have slightly larger radii and therefore probably a higher fraction of light elements, hydrogen. And then we have a couple of smaller planets that seem to be very compact and will have less gas. And actually, if we look at this as a sequence, we have the density here and the temperature here. So the innermost planets are actually to the right of this diagram. It's a bit odd because it seems that it goes up, it goes back down, and then it goes back up. So it's quite a challenge to explain this in terms of system formation. And of course, we'd like to understand really what's in the atmospheres of these planets. And that's why we have an ongoing JWST program that will study 3 of these planets in more detail. Okay, next highlight. We looked at a star called Nutu Lupi. Now, if a star has a name, you all know what that means. It means that it's visible actually to the naked eye. So this is a very bright star, 5th magnitude. It's solar type, very similar to the sun, and it was known to host 2 transiting small planets, one with 1.6 and one with 2.9 Earth radii at sort of 10 and 30-day periods. And from radial velocity measurements, there was a sign of a further out planet that seemed also to be there, but it was not known to transit. So CHEOPS were very good at measuring radii of planets. Let's go and measure these in much more detail, more precisely, and try and understand what these inner planets are composed of. So we went ahead and we did that, observed first a couple of transits of planet B. They're exactly where we expect them. Then we went ahead and observed transits of planet C. They're a little bit deeper, the planet is a bit larger. In the second one, something strange happened, but we quickly understood it was actually planet B was transiting just before planet C. But then we went ahead and we observed planet C once more. And that's the light curve that we got. And so we were like, oh, what's that? Okay, so it took took a little bit of scratching and thinking until we actually understood what was going on. What's happening is that actually isn't just planet C that's transiting, it's also the outer planet that we had just an indication from radial velocity that it exists, but we had no idea whether it would be transiting. It actually turns out that what happens is we have planet C starting to transit, and then planet D is starting to transit. And planet C is ending its transit, and the transit of planet D doesn't end before the end of the observations. So we went and we reconfirmed this, and it's really the case that what we're seeing here is a transiting exoplanet with an orbital period of over 100 days around a naked eye star. So of course, this is a fantastic planet. Once again, you can see the composition here. So both planet C and D, the 2 outermost planets, they are fairly large. So they do contain a bit of hydrogen and helium, while the innermost planet is essentially a rock with a slight addition of water. Okay. Now, these long period planets are, of course, really cool. And we'd like to have more of them. So what you can see down here, it's essentially, once again, one of these diagrams, planetary period against planet radius. And in yellow, I've put the planets that are well characterized, where we know mass and radius, or to good precisions, giving us a density of a precision of 30%. So you can see that to the right, in the right part, the blue part here is that we don't really have many well-characterized long-period planets. Now what we can do is we can actually use the data observed by the TESS mission. I don't have that, okay. So let me explain it to you then. So the TESS mission is an American mission that is sort of an all-sky transit survey. And what it does, it scans sections of the sky always for 30 days, one after the other. So it will give us photometric data of a duration of 30 days, and then it will move on. And it will only come back to the same field 2 years later. So what this data gives us for long period planets, it gives us, at best, orphaned single transit events. And sometimes we reobserve a transit event, but 2 years later. So with that, of course, we cannot constrain the planetary period other than knowing that it must be a multiple of these two transits. And then we can take either CHEOPS for low mass planets or ground-based observations for larger planets and confirm and try as many orbital periods until we confirm it. And this is what we did for this star here, HIP 6918, for example, a K star that here I've got a picture of TESS, that has 2 small planets that were observed by TESS. So here's the TESS data, that's what it looks like. And so in the first season, that's 30 days, taken in 2019, well, we see the deeper transit, the larger planet appearing twice. So there's still 2 or possible periods. We don't know if there was another transit down here. But we know at maximum the period is the length between these 2. And we see an individual orphan transit here with a different depth. So this must come from a different planet. It was observed again in 2021. Now the period of the shorter period planet here, the dark green one, was uniquely identified to 21 days. And there were just some possible aliases possible for the green one. And there was another observation in 2021 in November that didn't show a transit of that green one at all. So it must be a relatively long period. So we went with CHEOPS and we observed, these are the possible period aliases. We kind of went by probability and just scanned them one after the other. The first one was flat. So no, that period was rejected. Next one, also rejected. Also rejected, yay, we got it. So we actually identified in the end the correct period to be 52 days for this planet. So here we found a system that is not at all as compacted, a system that has sub-Neptune at 20 days and one at 50 days. So quite a different architecture from the one I told you before. And this is not the only one. So this was a press release that came out about a year ago, where we published 4 of these planets, 4 of these individual planets here. All of these are sub-Neptunes. Okay, we'll take a sip of water and then I'll be talking a bit more about the planetary atmospheres. All right, because we're using CHEOPS not only to measure radii and discover long period planets, but we can also use it to study close-in planets and study their atmospheres. So why do I say close-in planets? Well, it's simply because the signal to noise for any kind of atmospheric feature is much enhanced for a planet that is close-in and a planet that is large. So here we're really looking at these hot Jupiters, these kind of planets, right? They're really hot, they're really large, they have big atmospheres. And now here we're taking the transit technique, but we're going a step further, right? When we're observing just the transit, well, we observe this part here, planet going across. Now what we can do is we can actually observe the system, especially if it has an orbital period of just a couple of days, all along its orbit up to occultation, when the planet will pass behind the star. And now this, of course, will then allow us to measure the total flux coming from the system and infer something about the flux coming from the planet. So what we get from the occultation event itself, well, we get measurements of the flux coming from the planetary day side. These are pretty short observations, just like transits, a couple of hours, and they're pretty easy to handle because we have a very clear defined shape. And then we can do the whole phase curve thing. These are, of course, much more expensive observations because they take several days of observation time, but they do give us more information because they give us the longitudinal flux distribution. But here, a key important thing to remember is the CHEOPS passband. You can see it here in dark. So we're really smack in the optical. And now I've overplotted here just a couple of black body curves. One for the coolest hot Jupiter that we're studying, just at about 1,000 Kelvin. Now here, the black body is completely outside the CHEOPS passband. So anything that we're measuring must be reflected starlight, right? We don't see any thermal emission from the planet in the optical. On the other hand, this is the hottest planet that we observed. It's really a smoking 4,500 Kelvin on its day side. It's really an extreme object. And here you're seeing that actually we're right at the CHEOPS passband. So for this object, what we're going to measure is the thermal emission. And then the reflected light is just a small added effect. But then, of course, most of the planets, they're between the two. So just have a look at the, I'm making this appear, have a look at the yellow curve here. So for most planets, we do have a combination of these effects in our measurements. So what it is, I've kind of alluded to this, so let me go a little bit fast. What we can measure in the optical is that we measure the scattered light that gives us the geometric albedo and the phase function of the exoplanet. So it will look something like this. This is a measurement from Kepler. And if we look at the thermal emission, if we have these very hot planets and we get a phase curve, well, that tells us about the energy in total, the total energy budget of the planet and its bond albedo and the heat redistribution from day to night side. And we can even constrain a temperature map for the planet from a phase curve. All right, so what did we do? Well, we did occultation observations for a total of 21 different targets. I will not show all of them, just a couple of highlights. And we did those more expensive phase curves for 5 targets. Here's our population, our target sample. What I'd like to highlight here is that I haven't made these stars here blue because I like blue. But here we're really looking at a set of A-type planet host stars. And if you look at the planetary temperatures for these stars, well, they're really highly irradiated. So here we're looking at some very extreme systems where we're having this gas giant that is bombarded by an A-type star. These planets have orbital periods of 2-3 days, and they reach day-side temperatures of over 3,000 Kelvin. And I'm going to start with these. So that's kind of our sample. Yeah, they're great targets actually because the stars are bright. They have a high thermal emission. These planets are very hot. That gives them a large contrast, and that gives us a lot of signal to measure. So that's why we started with the most extreme one. The brightest one was 189. That has a visual magnitude of only 5.6, so it's perfect for a small space telescope. And so those were our first 4 science observations with CHEOPS. We can see here, these are 4 individual occultations of the planet behind its host star. And what we measure consistently is a depth of around 80, 85, 86 parts per million. And then we can, of course, combine them and we get a very nice, very clean detection of the occultation of this planet. And just, I like to highlight this, right? This was only 48 hours of CHEOPS observing time, admittedly on one of the most suitable targets. But the drop here that you're seeing is exactly the same amplitude as the drop of an Earth analog across the sun. So if we ever want to detect another Earth, we have the precision. The thing that's left now is to find the place to look at. But that's a whole other talk, and you should invite somebody from Play to tell you more about this. Now we're going back to atmosphere. So because this worked really well, we went and we observed the full phase curve. And so this was analyzed by Adrien Delin, who is a postdoc in Geneva. And you can see here, we observed the whole orbit. We cut off the transit because it kind of goes all the way down to the bottom there. And we have a very enhanced coverage over the occultation. And what we're seeing here actually is that the phase curve peaks right at the occultation, which tells us actually that the day side is heated very, very, very efficiently up, and not a lot of the heat makes it over to the night side. And essentially the heat doesn't really even get transported very far in either direction from the substellar point. What's also interesting is that the occultation is really deep. And even if we stretch everything to the maximum, it's really difficult to explain it only with thermal emission. But it seems that at least we have somewhat of a relevant geometrical albedo, which is a bit weird to understand. And I'm very interested in your ideas because this thing has a temperature of 3000 Kelvin. So we cannot really imagine any cloud condensate sitting in this atmosphere. All right, let me go to a different one, Mascara 1. Again, an A-star. Here we observed 3 occultations with CHEOPS, but we also had a Spitze phase curve, which is fantastic because that constrains us the thermal emission from this planet. And you can see the two next to each other here. On the top, that's the Spitze phase curve, the Spitze occultation. And down here, that's the CHEOPS occultation. Of course, because this is a planet highly irradiated, hot, it's emitting in the infrared. Well, this is huge in the infrared, that's at about 3.6 micron, but in the optical, it's much smaller. But still, we have a very good measurement. You can see the precision here, and we're actually more precise than Spitze. I just like to mention that occasionally. But of course, Spitze is fantastic, and it even gave us this beautiful phase curve that we can use to constrain the thermal energy from the planet. So what we did is, well, we computed a model emission spectrum. This is just thermal emission that has, and we compare it to 2 data points, the Spitze measurement here and the CHEOPS measurement down here. So to say anything, well, we have to zoom into the CHEOPS measurement. You can see it here. And what you see in pink or purple, that's the predicted thermal flux, assuming a realistic planetary emission spectrum. And what you see in black, well, that's our measurement. So we do again see some enhanced flux from this very hot planet. And once again, we find the geometrical albedo of about 0.2 that we need to explain this. And we're still a bit at a loss of what that might be. Okay, next one. KEL-20. KEL-20, once again, ultra-hot Jupiter around the bright A-type star. This one was observed quite intensively also with the TESS satellite that observes sort of between the optical and the near infrared. What I'm showing you here is the combined CHEOPS measurement on the top and the combined TESS measurement, on the bottom. TESS, we get a beautiful phase curve. With CHEOPS, we get a very clear detected occultation. But what was actually curious for this planet is that when we actually didn't combine all the measurements to make one phase folded light curve, but we plotted them one by one, this is what we got. So you can see in blue here, these are the CHEOPS measurements. And you see they kind of have this trend upwards. And there they make this little bump here. Now I'm very cautious about this because it's very easy to have measurements that kind of scatter between 1.5 sigma. But then looking at the test data, we see exactly the same kind of slope here and here. So this kind of gives us some, that I like to call it intriguing signs, that there is indeed something changing from one changing in the occultation depth with time, which could mean that there is a change in the thermal emission from the planet or in the reflected light. And once again, if we actually just, take the bulk values and we once again compute the geometrical albedo of 0.2 for this type of planet. So I am starting to see a pattern here. Okay. So let's go to the slightly cool hot Jupiters. So we only like 1,400 Kelvin. Now here we're in this part where we're not contaminated in our measurement by thermal emission. We're really just seeing the reflected light. And now this allows us to much more precisely and without any assumption, just measure directly the geometrical albedo. Those of you working on exoplanets, I'm sure you know these two planets there. They're kind of the transiting exoplanet superstars. They're very bright systems with very well characterized planets. And then we can say, well, are there any reflective clouds on the day side of these slightly cooler planets that would boost the reflectance from their day side? Okay, so we went and observed these two planets. These observations were much more time intense than the observations of the ultra-hot Jupiters, and the signals are much lower. You can see down here the one for HD 209. That's a composite of 10 individual CHEOPS observations, and you see the depth here, that's only 20 parts per million. But we detected very clearly, and we find that this is a fairly dark planet with a geometrical albedo of less than 0.1. And very similarly, this is work carried out by a PhD student, Andreas Krenn. Here we see the occultation depth similarly very low, and the geometrical albedo also clearly below 0.1. So no, actually they don't seem to have any reflective clouds in their day side. And in fact, their atmospheres are compatible with what we'd expect from Rayleigh scattering in an atmosphere that is just where the opacities in the optical are basically dominated by the sodium in the atmosphere. Now, all right, so in the last, maybe you give me 10 minutes. In the last few minutes, I'm going to show you, I think, 2 more results that I find very intriguing as well. And here now we're not anymore looking at these ultra hot ones, but here we're looking at a planet called WASP 76. It's it's still a pretty hot Jupiter at 2,100 Kelvin, but less extreme. And this guy, we really bombarded it, right? We took 3 phase curves, 20 occultations, and 6 transits. And actually what we realized there is that, with a little bit of scheduling and timing flexibility, we could actually stitch together occultations and transit observations and sort of create partial phase curves from those. And that's a result that came out just earlier this year. That should actually be a 24 down there. And that's the phase curve that we get. And what is odd is that we're clearly seeing a weird bump before the occultation. So we're seeing some kind of asymmetry. And its shape is different from what we'd expect if the planet just has a hotter area on its eastern limb, because then we'd expect it to be less pointy. So the interpretation that we propose for this is that perhaps at the very specific part in the planetary atmosphere, there are small cloud particles. And what we're actually seeing is a glory effect, where it's a backscattering effect at these clouds that then create this interference pattern, and that really boosts the brightness in a very specific part of the planetary atmosphere. This is a proposition. We're observing, of course, this system with a lot more CHEOPS data, exactly to really resolve the shape of the phase curve around here. Because I think there's still a bit of improvement that we can do, especially in this area. to really nail down the shape of this anomaly. Okay. And now I think that's the last one that I have for you. This one is WASP-12. Now WASP-12 is a beautiful system. Again, we're looking at a pretty highly irradiated planet, 2,600 Kelvin. The interesting thing here, this guy has an orbital period of 1 day. So it's extremely close in. It's actually the only planet that we know is spiraling into the host stars, and some tens of millions of years, it's actually going to be gone and ripped apart. So we're really observing the system at the end of its life. But being so close to the star, well, of course, the planet is suffering tidal interactions, and it's actually being elongated. Now, we understand that it's probably elongated just from looking at, you know, the physics and the strength of the tidal force, yeah. But how much elongated is it? Well, we went with CHEOPS, and once again, we made an absurd amount of observing time on this 21 transits and 25 occultations, stitching them again together to make phase curves together. And what you can see here all fit together and binned is the CHEOPS phase curve of WASP-12. So what we're very clearly seeing is several things. We see a clear bump here that is, and we also see an asymmetry. And what we're on top of that identifying from the transit and also from the phase curve is some sign of the planet actually also deforming. So we don't just see the emission from a circular planet, but the emission modulated by the planetary surface. So what we find here is that it has a hotspot that is shifted eastwards. So this is a sign of winds transporting the material. This is sort of expected for a planet in this temperature range. We find a lowish geometric albedo again. But more interestingly is we constrain the tidally deformed shape. And we find that it is 20% larger in the radial direction, looking from the stellar core, than it is in the other direction, for lack of a better word. And I can use this. This is work by a postdoc, Babatunde Akinsami. I can use this to constrain the second love number of the planet. And it seems to be, I mean, here you see it, the uncertainty is 0.5. So this is just 3 sigma. But it seems to be very similar to that of Jupiter, which makes sense. This gas giant actually has an internal structure that is at least in first order similar to that of Jupiter. And on top of that, well, it looks a little bit like a rugby ball, which is cool. All right, so with this, I would like to mention this because I know that here in the room, there's a lot of people not working on CHEOPS yet. CHEOPS is open, right? We have yearly calls for guest observers. Anyone from any institute can apply. There are absolutely no restrictions in terms of countries or institutions. You can apply for observing time. I mean, you can talk to Neda if you need if you want an example of somebody who's done it. And you can also observe get observation time between cycles. If you have a very exciting target, you can always ask for discretionary time. And especially for the early career scientists here, the requirements on these discretionary programs are relaxed. So even if you don't have the newest, most exciting, unique target, you can still submit a proposal. And if you're an early career researcher, if it makes sense, you can get discretionary time on CHEOPS. So I think this is something that's perhaps not quite as well known as it should be. So please do use that. I think that would be really cool. Of course, if you have any more questions on CHEOPS, feel free to come and talk to me. With that, I'm at the end. I haven't terribly overdone it, I hope. And I'd like to thank you for listening to 1 hour of exoplanet science. And yeah, I'm looking forward to discussing with all of you a little bit more.
Thank you so much, Monika. Any question?
Thank you for the talk. I have an outsider question. How is it possible that we can detect atmospheric phenomena like the glory effect more easily than exomoons? For me, this seems very counterintuitive. Can you comment on that, please?
I can comment. A lot of people have searched for exomoons. I think the fact that we can study atmospheres really well is that these ultra-hot Jupiters, we have these ultra-hot Jupiters, they're great. They have short orbital periods. So they, we have a phase curve in one day, essentially. So we can just take our telescope, can stare at it for 1 month. We have a lot of signal to noise. Exomoons are probably only existing around long period planets for dynamical reasons. So we actually need, to get to a signal to noise that is acceptable, we need, let's say, 10 transits of a long period planet. And that just takes a lot of time. And the scheduling of that is much more tricky because the target isn't always visible. And then exomoons have this annoying thing that they move around the planet. And so we can't just say, okay, we phase fold 20 transits and there will be one exomoon signal coming up, but that exomoon transit is going to move left and right of the planet because it goes around the planet. And so we don't easily stack things up. And that's why I think exomoons have been really tricky to find. What we don't know yet is the size distribution of exomoons. So we don't know if they're all the size of our moon, then they're also really, really small and create really tiny signatures. So voila, it's just, that makes it a bit tricky.
Any other question?
Okay, thank you. Sorry for the very naive question. At some stage, you have this, sorry, the phase curve with a bump and then the occultation. And maybe you said it and I missed it, but is there a reason why the occultation actually goes right at the same level at the beginning of the bump? Seems to me. Yeah. The occultation level seems to be exactly at the same level as the initial curve. That's why I was...
Yeah, that makes sense.
For that.
Yeah, because... so remember, these planets are extremely close to the host star, so they're tidally low. So we have one side that is hot and one side that is cold. When we're in the transiting configuration, we get the emission from the cold side. So basically 0, because it's very cold. Now, that sets the point that sets the flux level here. And then we rise in flux until we hit in front of occultation. And so during occultation, we go back down to the flux of the star alone. So there are actually, if you look very closely, you see that the model isn't completely at 0 here, and it's completely at 0 here. This is a tiny little difference. For some planets, the difference is more pronounced, and especially if you go further in the infrared, because that's the temperature, the thermal emission from the planetary night side. But because that is so low, it's basically as if the planet wasn't there.
Yes, thank you very much. I appreciate you advertise the GEO program because people have to be aware they can apply for this kind of observation. And NIDA is a good example of someone who proposed some very interesting observation as a GEO and got observed in time for a very interesting planet without being involved in the CHEOPS science team. I want also to ask you a little bit more details on the extension of the mission, because you explained us that the mission has just been extended to until 2026, and even there are positive expectation for until 2029, in fact. So what are the new questions that will be addressed with this extended mission? What are the expectations with this extension?
Yeah. So yeah, that's correct. We've been, I think, pretty much all of the results I show were from the nominal mission. So of course the GTO program has evolved a little bit towards the mission extension, and from particularly from, I think, from most aspects of the results that I've presented, is that we're going to go more towards key targets. So this one, for example, we're going to spend, I don't want to say an absurd amount of observing time, but a large amount of observing time, because we really want to measure those features in as much detail as possible. And I think we're spending less time in doing especially for these occultations, in doing a broader survey of properties. We're also observing intensively one of the cooler hot Jupiters, hoping to get a fully scattered phase curve. So of course, also that takes a lot of observing time. But then going back to things that are related to the smaller planets and the longer period planets, here we're really looking up systems where we suspect that there are longer period planets, resonance systems where we expect that there are longer period planets. And those systems where we have indications from previous or from other observations that there are longer period planets, we also follow them up quite intensively. And then there is one more aspect in the extended mission GTO, is that we also start exploring the synergies of CHEOPS with other space missions, most importantly ESA space missions. So we have 3 observing programs. One that was defined in collaboration with the Plato team that goes after Plato targets and actually does pre-Plato transit observations of these targets. That helps us understanding the dynamical architecture of these systems better. And then there are observations for aerial that are there to characterize the photometric behavior of some key aerial targets, and also just to set transit ephemerides, because when aerial will come, some of these smaller planets, they will not have been observed for 10 years. And it's important to do these observations to make sure that aerial will know when to point at these planets to have a good transit ephemeris. We're also observing simultaneously with several JWST programs. And that's something I haven't been able, I'm going to show you one plot on that, because I really find it quite telling. I can find it back. Here we go. Okay, so there's, for example, there was this JWST measurement that came out about a year ago. And you can see a beautiful transmission spectrum in the infrared. And you see 2 models. You see the blue one, this is an Earth-sized planet. Huh? This is a water-rich atmosphere. And you see the orange one. These are star spots. Now, if we had a very precise measurement right here at the blue end, we would actually be able to distinguish these 2. And we'd be able to actually say with confidence whether or not this planet has a water-rich atmosphere. And so these type of things are also things we're exploring with CHEOPS.
It was not a prepared question. Also, you showed. Thank you.
I didn't talk about transmission spectra, so it would have been too much of a stretch.
Any other question?
I have maybe a naive question, but so you saw the effect of the tidal forces on this planet, but it seems that it's really strong. So I know that this planet is very close, but I was wondering, can we imagine a scenario where the planet is rotating so fast that there is a deformation, like the shape has changed because of that, and maybe it's related to the formation? Well, actually, probably these planets would have migrated. So I don't know what do you think?
For yes, but not for this type of planet. So this planet, we expect that the rotation period of the planet is set to be its orbital period. we do actually see a slight difference in the two axes, but I don't think the data are quite precise enough to say anything about that. What we are looking at is long period planets that are not tidally disturbed by their host star, but they might rotate really fast because Jupiter rotates really fast. And Saturn is also pretty oblate, flattened. And that we can actually detect in transit light curves. And so this is one of the things that we're trying to do as well.
Thank you.
Any other question? If not, let's once more tell thanks to Monika.
So since it's so I will switch to French. C'était la dernière le dernier séminaire de l'année. Je voudrais vous remercier tous en ligne et ici de venir, d'être venus. Je voudrais remercier Jean-Baptiste Foubry qui va donc donner sa place à Florent Leclerc qui va co-organiser les séminaires avec moi à partir de septembre. Et voilà, bah, merci. Je voudrais remercier aussi la direction de financer et le travail remarquable de Chantal Levaillant que vous n'imaginez peut-être pas, mais qui aide énormément à l'organisation de ces séminaires. Donc, retour le 20 septembre avec Angela Adamo de l'Université de Stockholm. Et merci beaucoup à Monika pour ce superbe talk.
Merci beaucoup.
Bonne journée.
Bon.